up to now, in our look at stoichiometry, we've only been doing mass to mole conversions before we get to the mole to mole or molar ratio conversions. Well, stoichiometry goes far beyond that, and in this lesson we're going to go beyond that a little bit. We're going to go from mass to mole conversions and mole to mass conversions to particle to mole and mole to particle conversions, and also volume to mole for gases and mole to volume conversions for gases. Here's the homework problem you were assigned to do. It's 16.8 grams of copper placed in a solution containing 25.65 grams of silver nitrate, plus the percent yield if 12.10 grams of silver is recovered. So we want to start with a balanced equation to evaluate what's going on here. Let's see, we've got copper, and the symbol for copper is Cu. And metals, except for mercury, are always solid, so that's a solid. And it's in a solution of silver nitrate. Silver is Ag and nitrate is NO3. Silver's charge, if you look on the, I can find my set of references here. So silver's charge is 1 plus. And then you look on the common ions list. For this class, you can look on the common ions list and see that nitrate has a 1 negative charge, so a 1 plus and a 1 negative, those cancel out, and that's balanced with 1 of each. We also need to know the physical state of silver nitrate. For that, we go to the solubility rules. And the solubility rules state that all nitrate compounds are always soluble and no exceptions. So that's aqueous. And then if we have an element that's by itself and a compound that has something like it, then this is, if there's going to be a reaction, it's going to be single replacement. And when I say like, I mean that this is a metal and that's a metal. So we need to know if copper will displace silver. Copper is located here and it's higher on the activity series than silver is, so theoretically at least copper should displace the silver. So that means the copper will kick out the silver and join up with the nitrate, leaving silver by itself. And in fact, the problem says silver is recovered, so that makes a lot of sense. Silver is going to be a solid because, again, it's a metal. And we need to know the charge on the copper and the nitrate. Now, just for the record here, just to reiterate something I told you before, elements that are by themselves are only bonded to themselves. When I say bonded to themselves, like oxygen is bonded to itself to make oxygen in the air, O2. Elements by themselves have a 0 charge. So the actual charge on copper when it's by itself is a 0, and the actual charge on the silver by itself is a 0. But now the copper in a compound either has a 1 plus charge or a 2 plus charge, and we need to know which it is. You look on that periodic table that has the different charges on there for you, the possible oxidation numbers. Copper has either a 2 plus or a 1 plus charge, but if you look at the activity series and examine it carefully, it tells you that at least for us, when we're doing single replacement reactions, copper in a compound becomes copper 2. So that's going to be a 2 plus. Nitrate is on the common ions list. And on the common ions list, it shows you that nitrate has a 1 negative charge. So I'm going to need 2 nitrates to balance this formula. So to balance this formula, then I need to put a parenthesis around the nitrate and put a subscript 2 afterwards to show that I have 2 nitrates to balance out the charge of 2 plus on the copper. All right, now that we have the formulas balanced, we're not going to touch those formulas again. We're going to just balance the equation using coefficients. So let's make an atom inventory here. And in this class, you're required to do an atom inventory every time you balance an equation. Even if it's already balanced, you'll write an atom inventory to show me that you know that it's balanced because I'm from Missouri. It doesn't make sense? Look it up. So copper, there's 1 of those, and there's 1 silver, and 1 nitrogen, and 3 oxygens. On the other side, we've got 1 copper, 1 silver. we have 2 nitrogens. The parentheses here means that everything inside is going to be multiplied by what I have outside here as a subscript. So since the nitrate had 1 nitrogen, but we have 2 nitrates, that means overall we have 2 nitrogens and we have 6 oxygens. So I want to do something with coefficients that will balance this out. So I'll go back over here on this side, and the species that contains the nitrogen, I want to balance oxygen last. So I'm going to start with nitrogen. The species that contains the nitrogen, we can put a coefficient 2 in front of it to give me 2 nitrogens, which is going to change the number of silvers and nitrogens and oxygens. And now we're going to have 2 silvers and 2 nitrogens and 6 oxygens. It's 2 times everything in the formula. On the other side now we need to fix the silver, so we'll put a coefficient 2 here, and that'll give me 2 silvers and everything's balanced. Alright, so we have 16.8 grams of copper. We're going to put that over 1. Whenever you're doing stoichiometry, you always want to put your starting amounts over 1. And we want to convert to moles in order to go from one chemical species to another. And we're going from this chemical species to this chemical species. In this case, we'll do another equation in a minute where we go from this one to this one. For now, we're going from this to this. So we need to get this into moles because the ratio between copper here and silver here is in moles. Now, since there's only 1 copper, calculating the molar mass for copper is really easy. All we need really is the atomic mass. And the atomic mass for copper is 63.546. And since the definition of molar mass is the sum of all the atomic masses of all the atoms in the formula in units of grams, if we only have 1 copper, then we only need it 1 time. So that's grams of copper equals 1 mole of copper. And for me, every time you write molar mass, when you do your molar mass calculations, I want you to finish it with this equality statement. The equality statement is emphasizing the fact the way we get conversion units is to have 2 things that are equal. That's what a conversion unit really ought to be thought of, and it sure makes your stoichiometry a lot easier when you think about it that way. Because now I've got units of grams and copper on the top here, and I just choose the side of the equality statement that matches the units and species and put that on the bottom. So we have 63.546 grams of copper, and on the top I have 1 mole of copper. Now we want to simplify by canceling out grams and copper. That's what dimensional analysis is, and this process of setting up the problems like this is called dimensional analysis. So we now have copper in moles, and we can go from copper in moles here to silver in moles over here. So if we have 1 copper, we're going to just put 1 mole of copper here. And we have 2 moles of silver over here, so we'll put 2 moles of silver on the top. Well, now we've got silver in moles, because I can cancel out moles of copper top and bottom here. So all I got to do now is convert this from moles of silver to grams of silver. And again, in this case, we're kind of lucky. It's kind of simple. We're going to be using just the atomic mass for silver, 107.8682. 107.8682 grams of silver equals 1 mole of silver. And we're going to build a conversion unit. Now, for this conversion unit, moles are on the top here, so this time I need the moles on the bottom here, not on the top like I did in this case. So it's 1 mole of silver and 107.8682 grams of silver. And I want to simplify. Now, what students a lot of times will do, and I'm trying to make sure that I'm as clear as possible and help you not to do this, is they want to look at this 2 here and think I need 2 silvers down here. That is not the case. You only use the number of silvers or coppers, nitrogens, and oxygens that are in the formula. The coefficient has nothing to do with the molar mass. The coefficients have everything to do with the molar ratio. That's the point. We use the coefficients in this step here. We don't use the coefficients in this step here. Alright, so now we're ready to do the math. We're going to take this number and multiply it by that number and multiply it by that number. We're going to hit enter, and then we're going to divide by that number. And when I did this in my calculator, I got 57.035 39987. And the units we have left are grams. The species we have left is silver. We want to round off to the correct number of significant digits. We're going to look at all the measured and calculated numbers. Measured numbers are those that are actually measured. So this copper could have been weighed on a balance. That's a measured number. And these numbers here where we calculated, or they were actually calculated by somebody to get them on the periodic table, this number and this number are calculated numbers. Okay, so those are our calculated and measured numbers. All the numbers are counting numbers. So we don't use the counting numbers for figuring out significant digits in multiplication and division. We only use the measured and calculated numbers. And among these measured and calculated numbers, this is the number that has the least digits. We want to match the final answer to that same number of digits. So we count 1, 2, 3. Those are our significant digits. Underline this, draw an arrow, and round it off to 57.0 grams of silver. Okay? That's the first mass-to-mass stoichiometry problem we need to do. The second one is to take the amount of silver nitrate in the problem and calculate our way to the silver. And the amount of silver nitrate that was in the problem was 25.65 grams. So we'll start with 25.65 grams of silver nitrate. And we want to convert it into moles, just like we did here. But now we've got to calculate the molar mass of silver nitrate. That's a bit more complex than we had up here. With silver nitrate, we've got to add the atomic masses of all the atoms in the formula. In the case of just a copper or silver, that's pretty simple. But with this, it's a little more complex. Well, silver's atomic mass, we said, was 107.8682. Nitrogen's atomic mass is 14.0067. And oxygen's atomic mass is 15.9994. We're going to multiply these by the number of those atoms we have in the formula. We've got 1 silver, 1 nitrogen, and 3 oxygens. And notice I'm keeping all my digits lined up very neatly. That's kind of important because it's going to help us when we, well, in this case it won't matter. But if you have any empty slots to the right, that's how you figure out how to round off for addition and subtraction. So the rules for significant digits for addition and subtraction are different than they are for multiplication and division. In this case, we won't have any empty slots. Let's see. So we've got 15.9994. We're going to multiply that by 3, and we get 47.9982, yes. And now we're going to add that number to the other two numbers, okay? So we're adding that to 14.0067, and adding that to 107.8682, and we get 169.873. Well, what you're going to see here is that when you line your digits up neatly, there's kind of an empty slot right there. Now, the reason for that is this calculator I use on my computer doesn't give me all the digits. It's kind of rounding things off. So there should be a digit here. Let's see, this should be 11, right? And so that should actually be a 2. Is that what you guys got?
No, we got 8731.
Oh, 3. Okay, I got it. Yeah, you're right. 31. Okay. So you just need to be careful to make sure that what you have is showing you the right number of digits. Okay, my little calculator or the simulator I have on my computer, it doesn't give you all the digits because it's trying to make it easy to see on the screen. All right. So anyway, this is grams of silver nitrate, and we're going to write that or state that as being equal to 1 mole of silver nitrate. Okay, and from that, then we can build this conversion unit here, 169.8731 grams of silver nitrate, and we got 1 mole of silver nitrate on the top. I'm going to simplify. I'm going to convert from moles of silver nitrate to moles of silver, and there's 2 moles of silver nitrate and 2 moles of silver. going to simplify here. And now we've got to convert from moles of silver to grams of silver, and we already have the molar mass done right here, so we can just plug that in. Again, we've got moles of silver on the top here. We need to have moles of silver on the bottom, and this side here of the equality statement has the moles, so we'll put that on the bottom, 1 mole of silver, and the other side's going to go on the top, 107.8682 grams of silver. Cancel out what we can cancel out to simplify. And now we're ready to do the math. So let's see, 25.65 times 2 times 107.8682 I'm going to hit enter on my calculator, and I'm going to divide by this number. And I get 32.5751 320. Oh, I didn't divide by 2. You're right. Thank you. Divide by 2. Good for you. All right. So now it's 16.28756,601. All right. And that's grams of silver. Now, guys, if you aren't doing the math with your standalone calculator, and you have to use a standalone calculator on the test, if you aren't doing your math with your standalone calculator, if you aren't practicing these problems with your standalone calculator in class, when you get to the test, you may find something about your calculator doesn't quite give you the right answer because you haven't figured out how to use it. So you want to practice with that calculator as often as you possibly can. So don't just wait for me to give you an answer, okay? Now, of course, this is homework. You should have already done this. But if you haven't done this, and I'm showing you how to do it, you should plug it in your calculator yourself and see if you get the same answer. So if there is an error, like you guys caught me with the fact that I forgot to divide by 2, okay, then you aren't recognizing that you have a problem using a calculator. We need to get that straightened out before you get to the test. And this is the first test where calculator use is going to be really, really important. Before, almost everything we did, you could do without a calculator. Anyway, we've got 4 significant digits here in this number, and these other 2 measured or calculated numbers have, that's 7 and 7 there. So we want 4 significant digits, and round it off then to 16.3 grams of silver. All right, so we've got 2 different masses for... Oh, you're right. I still made the mistake there, didn't I? Rounded off correctly. There you go. Man, I'm just messing up all over the place, and Deja's just catching me on everything, isn't she? Good for her. All right, so what we want is the smaller number. All right, of these two masses here, we want the smaller number, okay, because the smaller number is our theoretical yield. All right, so this is our theoretical yield. All right, and because that's the theoretical yield, the species, just the chemical species we started with, is the limiting reactant. So the limiting reactant is the silver nitrate. Okay? So what we're going to do now is determine what our percentage yield is. And the percentage yield, we take the amount recovered, which is the actual yield. The amount recovered or collected, the amount filtered out. There's a lot of ways to say that, but it's the amount you get at the end is the actual yield. This is a theoretical amount. It's not an actual amount. What this is a number that if everything were perfect, you could get this amount out, but you can't get a perfect amount out. It's not going to happen. Nothing's going to be perfect like that. So for percent yield then, we're going to take the actual yield. In this case, it's 12.10 grams of silver. And we're going to put it over this theoretical yield, 16.29 grams of silver. And that answer, we're going to multiply by 100 to get a percent. So 12.10 divided by 16.29 and hit enter. And then multiply by 100. Okay, so you need to make sure you hit enter in between. And then we get 74.29 0.2787. You want to round it off to the correct number of significant digits. Well, actually, first I need to simplify. Notice the units cancel. Guys, if a percentage is set up properly, the units should always cancel. The species won't always cancel. We'll learn about that today, but the units will cancel. And so we want 4 significant digits, 1, 2, 3, 4, underline the insignificant digits. There's no units or species here, so this is a percent. We're going to round this off then to 74.28%, but we've got to say what the percent is for. And it's the percent yield in, for, or of silver. Okay, so actual yield divided by theoretical yield times 100. This is your unrounded answer. Underline the insignificant digits and round it off to that 4-digit answer. In this case, it's 4 digits. All right, so in stoichiometry so far, we have been doing mass-to-mass stoichiometry just to get you guys into the habit of how that works. Because, frankly, most of the math that's done with stoichiometry is mass-to-mass. It's pretty common to do that sort of thing in the lab. So with mass-to-mass stoichiometry, well, in fact, where we started was we had moles of one chemical and went to moles of another. Okay, that's where we started when we were doing this unit. And then we branched out from that to do mass-to-mass. So let's put it down in the order that we learned it, okay? We went from moles, when we first started this, we were calculating from moles of one chemical. Let's call this chemical A. Okay? And we went to moles of chemical B. Well, that's better than... All right. So, now how did we get from moles of A to moles of B? How did we get from moles of A to moles of B? Yeah, you had to have a balanced equation. From the balanced equation, we got a ratio called a molar ratio. So what we did to get from moles of A to moles of B was go through a molar ratio. Okay? And Chastity is correct. The way we got there was with a balanced equation. This required a balanced chemical equation. Well, it won't fit in there, so I kind of wrote it down below the box just to know that's where we got our molar ratio from, was a balanced chemical equation. Okay? Now then, once we started looking at mass, how did we get from mass of a chemical to the moles of the chemical?
The chemical ratios. Like the ones where you
That's what this one is. That's the chemical ratios.
What did you say? Where you gotta find
From mass to moles.
the molar mass.
Molar mass. So if we had mass of chemical A, and we want to go to moles of chemical A, then we need molar mass. Now, molar mass is used to go also to go from moles to mass. So once I get from mass of chemical A to moles of chemical A, and then you use the molar ratio to get the moles of chemical B, then I can get the mass of chemical B using molar mass over here as well. All right? Now remember, the molar mass is just the sum of all the atomic masses of all the atoms in a formula, written in units of grams. In this class, I require you also to write an equality statement. So you say grams of that chemical equals 1 mole of that particular chemical. Okay? So that's what we've been doing. But notice we got a bunch of other bubbles out here, don't we?
Yeah.
There's a lot of other things you can use stoichiometry for.
A, B, C, D, and E, right?
Yeah, a lot of these, yeah. Okay? Now, 2 of these you should already know about because we did a mole project for mole day. And it was part of the requirements for the mole project for mole day. One of them was how to get from particles to moles. Okay? So if I have particles of chemical A. How do I get from particles of chemical A to moles of chemical A? Huh?
It's like the gas constants, right?
No, that would be from volume to moles. We want to get from particles to moles.
Oh,
Okay.
Avogadro's number.
Avogadro's number. So the particle to mole conversion is using Avogadro's number. Okay? Avogadro. Come on. Yeah, I can't really fit Avogadro in this space. I'm just saying particle to mole is Avogadro's number. And the equality statement for Avogadro's number is 6.022 times 10 to the 23rd particles equals 1 mole of particles. Okay, 6.022 times 10 to the 23rd particles equals a mole of particles. Okay, and that's Avogadro's number. And so if I'm going to particles of chemical B, I can use that same equality statement. I can go from particles of chemical A using this ratio here, get to moles of chemical A, use a molar ratio to get the moles of chemical B, and use the Avogadro's number particles to mole ratio to go to particles of chemical B. Yeah, I kind of did write it small on here, but you want to hold it up close?
Rookie mistake, Mr. Tatter.
6.022 times 10 to the 23rd.
Yeah, y'all should know that. Come on. Really.
It says, I don't know what it
All right, here we go. What if we have volume of a gas?
Gas constants.
Okay, there you go. That's what that's going to be for. Okay. Now, in order for you to have volume of a gas, this is still going to be chemical A. Okay. We need the gas to be in STP. Okay. STP. Good. Standard. Well, it was part of the mole project. Everybody should have had that. Standard temperature and pressure. Okay. So what we call this is simply molar volume. Okay, molar volume. Molar volume you don't have to calculate. It's like Avogadro's number. It's always exactly the same. There's always 6.022 times 10 to the 23rd particles in 1 mole of particles. Well, with volume at STP, there's always 22.4 liters of gas in 1 mole of gas. Every time, all the time. You don't have to calculate it. You just got to remember 22.4. How hard is that? Hopefully not too hard.
We have to remember that.
Yeah, you have to remember that. 22.4, you got to remember it. Okay? That's liters of gas equals 1 mole of gas. Yes. It's for gas. All right? All right. So then we can go back from moles of chemical B to volume of a gas using molar volume as well. Because molar volume is an equality statement. With an equality statement, you can always build a conversion unit. So this is volume of a gas, chemical B, as long as we are at STP. All right, so this ratio here, 22.4 liters of a gas equals 1 mole, only works at STP. Okay? Now we're going to talk about particle and volume conversions to moles today. The last one over here we're not going to talk about until we get to another unit is for concentration of a solution. Okay? So, if we know the volume of a solution and this side of the mole map is for chemical B, we can get to the moles of that solution, the moles of the chemical in that solution, using molar concentration. Molar concentration. So we can get to the volume, or go from the volume of a solution for chemical A. Using molar concentration. And we'll get to that when we get to the solutions unit. A couple of units away. All right? Couple of units away.
I think that's beyond the scope of this class.
You think it's beyond the scope of the class? And you would be wrong. Okay. Anyway. So listen, guys. Pay attention. Listen. What are the two reactants in this problem? Chromium and hydrochloric acid. Which one of these two is the limiting reactant?
Chromium. HCl.
Read the problem carefully.
If we have
It's chromium because the X.
Yes, exactly. There's more than enough hydrochloric acid. Okay? You were right, Eric, but somebody else said something else, so I want to make sure everybody reads it carefully. You have more than enough hydrochloric acid. Basically, I've written this problem so you don't have to calculate a limiting reactant. Okay? I've given you a problem where you only have to calculate the theoretical yield. That's it. Okay?
Can you not do that too for us?
What now?
Can you not do that for us? Do the yield thing?
Well, you have to be able to calculate or determine the limiting reactant, but in this case, I worded it so you don't have to do it. Does that make sense?
Yeah.
All right. But you should be able to listen. You should be able to write a balanced equation. Please do that now. All right, we're doing stoichiometry, so we balance the equation first. Then you're going to build the calculation that you need. Okay, you already know how to do molar mass here on the left. The only new thing we have here is molar volume. And you know how to build a conversion unit because I've taught you over and over since Unit 1 how to build conversion units. With the quality statement, you build conversion units. Okay? So now all I got to do is do the math, right? You got the math? You got an answer?
I have an answer.
Have you calculated the answer?
Oh yeah, we got it.
Did you get 10.8?
Yeah.
Is that hard? Not really. It's the same stuff. It really is. It's the same stuff. Okay?
What?
We have to put the S.
Oh.
And it's easier because you don't have to calculate any molar masses. It's just 23.4 liters of a gas equals 1 mole of a gas. Boom. All right?
Yeah, we get it.
All right? Don't have to calculate a whole bunch, add up a bunch of atomic masses and multiply them by 2 and 3 and 4. Okay? You just got to know 22.4. That's it. All right? Everybody got that? Problem. Here's another problem. Solve this problem now. Let me give you one little tip. Molecules are particles.
Yeah, we don't discriminate. I got hungry on the way home.
Let's say we have a single replacement reaction that is producing a gas, and the single replacement reactions that produce a gas might be the halogens, or it could be a metal creating hydrogen gas. Let's do the metal creating hydrogen gas here, okay? So let's take some, I don't know, chromium, let's say we have 25.0 grams of chromium. And excess. Now, an excess means we have more than enough. Okay, that's all it means. More than you need, an excess, okay? So, an excess of hydrochloric acid so if in this case, what's the limiting reactant? Huh? What is the limiting reactant here? Yes, you do. You should know.
The excess hydrochloric acid.
Well, excess, you got, why would that be? Yeah, the chromium, because you got more than enough hydrochloric acid. That wouldn't be the one that stops the reaction. That's not going to be the one that runs out first. The limiting reactant always runs out. Hydrochloric acid is not going to run out because we got more than enough. Okay? So in this case, the limiting reactant is chromium. I've cut some of your work down like in half almost. Not about a third really, not in half. Okay? By just telling you we got an excess of hydrochloric acid. Guys, you got to know what this means, all right? Limiting reactant is the one that runs out. If you've got an excess of something, that can't be the limiting reactant. Okay? Let's add, the question then is, how many liters of hydrogen gas might be produced at standard temperature and pressure? As some people said in their Mole Day project, and everybody should learn from that, standard temperature is 0.00 degrees C. Standard pressure is 1.00 atmospheres. Okay? Okay? So what's the first thing we need to do? Standard temperature is 0.00 degrees C, and standard pressure is 1.00 atmospheres, ATM. A what? Dimensional analysis? Okay, well, until we got to do one other thing before we can get to that. What? Have to have a balanced equation. It's a balanced equation. Okay, so we're going to use the activity series of metals and solubility rules to help us solve this problem, okay? So, chromium. Chromium is just a metal, all right? And all metals except for mercury are going to be solids, okay? Here's chromium right here. Metals are anything from this side of the periodic table, where the stair step is, to this side, and only mercury is a liquid metal for us, okay? So this is a solid. And we're putting it with hydrochloric acid. The prefix hydro means I have a binary acid. Binary means it's only two elements. So we have to have hydrogen because all acids have hydrogen. So the only other part of it is going to be chlorine. So we're going to put hydrogen with chlorine. Hydrogen, if you look on the periodic table, has all those oxidation numbers for you. Hydrogen is going to be a 1 plus charge. Chlorine is going to be a 1 negative charge. And so we need one of each. That's hydrochloric acid. Now that's going to be in aqueous form. Acids really don't do much of any kind of work unless they're in aqueous form. At least for us in this class, we'll assume that to be the case. Now then, on the activity series, then we're going to look and see, will chromium displace the hydrogen? and chromium is located right here, and hydrogen in an acid is located here. So since chromium is more active, it will displace the hydrogen. So chromium is going to join up with a chlorine. That's a single replacement or displacement reaction, and the hydrogen is going to be by itself. However, when hydrogen is by itself, it forms H2, and that's going to be a gas. That's just something you have to know, that it's going to be a gas. So chromium, if you look on the activity series, it says that chromium by itself is just, see, it has no charge. It's a 0 oxidation number. But in a compound, it's going to have a 2+ charge. Okay? And we said that chlorine has a 1 negative charge. So to balance out this formula, we're going to need 2 chlorines. And the formula is CrCl subscript 2.
I thought it was 3 or 7. Why is it 3? Yeah, because
It's not 3+ because on the activity series it says in single replacement reactions, chromium becomes 2+. Now it could be a 3+ because one of the 2 oxidation numbers of chromium is 3+. So the question is, how do you know which one of these 5 different oxidation numbers it is? Well, the reason you know that chromium is going to be 2+ in a single replacement reaction is it says so right here. Okay? So chloride compounds are mostly soluble, no exception over here for chromium. So chromium chloride is going to be aqueous. If there's water around, a soluble compound will be aqueous, and since hydrochloric acid is aqueous, that means there's water around. So now we're ready to balance the equation. So we got chromium and hydrogen and chlorine. We're going to balance the equation. And we've got 1 chromium and 1 hydrogen, 1 chlorine on the left. On the right, we've got 1 chromium, 2 hydrogens, and 2 chlorines. So a coefficient 2 here will change the number of hydrogen and chlorines to 2, and we have a balanced equation. Now, once the equation's balanced, we're ready to do the stoichiometry. We're starting out with grams, but at the end we want to find out what the liters are. Okay, that's what the question's asking for. So we start with 25 grams of chromium. We need to find the molar mass, and since it's just chromium, that's pretty simple. We just use the atomic mass in grams, 51.9961. And we're going to set that equal to 1 mole because it is equal to 1 mole, and it makes it possible for us to build this conversion unit. So we can cancel units. Now we want to do a molar ratio, so we can go from chromium to the gas we're looking for. And that's a 1-to-1 ratio. So we've got 1 mole of chromium. I'll put that on the bottom here. I want to put 1 mole of chromium on the bottom here so that it'll cancel these units. And on the top, we're going to put the 1 mole of hydrogen. All right. Now we're ready to convert the hydrogen to liters. Okay? And we're saying that this is at standard temperature and pressure. So if we have moles of hydrogen, actually it should be MOL, not MO. Here's the molar volume ratio you need. You don't have to calculate anything. Okay? Which one of these 2 sides of this equality statement do I want on the bottom here?
1 mole gas.
Okay, 1 mole of gas, which is 1 mole of hydrogen. And what goes on the top?
22.4.
Liters of, because hydrogen is a gas, right? So you plug in the gas you need because this applies to all gases. Cancel out, simplify things, and do the math. Yeah, this isn't hard. This is easier than stuff we've been doing.
For real? Yeah.
10.77003852. 25.0 times 22.4. Oh, wait a minute. For some reason, it isn't showing up on the screen here. What's the deal with that? 25.0 times 22.4. Enter. Divided by 51.9961. 10.77 on this computer calculator, but on my calculator, I used a different calculator to get the longer number. So I've got 3 digits here and 3 here. So I want 3 digits in the final answer. That's liters of hydrogen. So I've got 10.8 liters of hydrogen gas. Okay? And that's as long as it's at STP. Okay? It's only 10.8 liters at standard temperature and pressure. If you reduce the pressure, the volume's going to expand. If you reduce the temperature, the volume's going to contract. So we'll find out about that in the next unit when we talk about gas laws. But that's why you have to have it at standard temperature and pressure, okay? That's the condition you need. Listen, that's the condition you need to use this molar volume ratio here.
Rounding off.
Yeah, I'm underlining these digits because those are insignificant. I looked at the measured and calculated numbers. That's this number, and this number, and this number. And of those 3 numbers, this one and this one have 3 digits. Those are the least number of digits. We want 3 digits in the final answer, 1, 2, 3, and we underline everything past that. Since I'm rounding off this 7 here, it makes this 7 here round up to an 8, and we get 10.8.
So that's the final answer. Like, we don't have to do anything.
That's the answer to this question. Because in this question, I told you in advance what the excess reactant was, and by telling you what the excess reactant was, hydrochloric acid, by extension, that meant that chromium was the limiting reactant. Okay? So you didn't have to figure out what the limiting reactant was here. I told you that. Let's do this one then. Let's modify the question a little bit. How many molecules of hydrogen will be produced? Yeah, molecules are particles. So instead of this ratio, we'll use Avogadro's number ratio.
What? I don't.
If we're trying to find molecules of hydrogen, then we don't need a molar volume ratio. We need a molar particle ratio, which is Avogadro's number.
So we'll set it up the same way, but where we put it. So what
Yeah.
you're saying is Molar Volume will put it out of the
Yeah. Yeah.
So we read all that. No, I said everything around. 22.4
In this previous problem, we went from the mass of one chemical to moles of the first chemical to moles of the second chemical and to volume of that second chemical. Okay? Now I'm asking you to go from mass of the first chemical to moles of the first chemical, moles of the second chemical, to particles of the second chemical. That's all I'm asking you to do.
Oh, okay. No, there is no. Oh, okay.
All right. If we have 25 grams of chromium and an excess of hydrochloric acid, how many molecules of hydrogen will be produced? Well, that just means we start with 25 grams again. Put it over 1.
Did we have to write that whole thing out? Yeah, I did. I didn't. I just put it all through my head. Mr. Taylor, did we have to write that whole thing out?
If you were doing this for credit, you'd have to write the whole thing out.
But we're not.
Do we have to put each one board
Square thing is like the X to the X.
Now, the one thing listen, guys, we really need to write down whatever your equality statements are so that you're justifying your conversion unit, okay? I didn't write it down here, but that's what you need to do. That's just something you have to memorize, okay? You just have to memorize that 22.4 liters of a gas equals 1 mole of a gas, and you have to memorize, which you already should have done, take 6.022 times 10 to the 23rd particles. Particles are molecules or atoms or electrons, whatever they are, of something, equals 1 mole of those particles. So in this case, the particles are molecules. Okay? Cancel out everything we can cancel out. And do the math.
So our little thingy is going to be molecules of H2?
That's what it's asking for. How many molecules?
If we have the E24 thing on the end of each song, do we have to write that?
What do you have?
I got it.
Mr. Cheddar, I think I figured out how to do it, but I don't know how to,
Well, just hold on.
Do we round it? Mr. Cheddar?
Yeah,
Hush.
he's correct.
Okay, well, how many places do we round it? 4?
Yeah.
I got that, but whenever I hit enter, it doesn't give me the answer. It just gives me the same thing.
Yeah, that's, oh, you're trying to multiply that times something?
Uh-huh.
So you want to multiply that times 25 times 25.0 equals, oh, I don't know. I don't
And then
know.
there's another thing down
Yeah,
here.
that's probably the easiest way for you to do it here. So 25.0 times 6.022 times 10 to the 23rd power equals, and then divided by 51.9961, and that's the answer.
Oh,
Okay?
Mr. Cheddar.
Yes.
This is what I got. I got 20.923.
Well, you got a syntax error. Probably you put a decimal in the wrong place or used the wrong exponent here. Okay. Quiet, please. Quiet, please. No. Sit down for a minute. Quiet, please. Not right now. Sit down, please. Quiet, please. Quiet, please. Quiet, please. Thank you. All right. Percent composition. If we have the molar mass of any chemical, let's see, we did the molar mass for silver nitrate here, okay? Let's just use that as our example. We have the molar mass of silver nitrate, okay? It's right here already. The way you get the percent composition, listen carefully, is to take this mass of silver and divide it by the total mass. Multiply by 100. So the percent of silver in silver nitrate is 107.8682 grams of silver in 169.8731 grams of silver nitrate. Okay? That's just the silver in silver nitrate. To get the total percent composition, we also need the percent of nitrogen and oxygen. Yes, 8731. 8731. All right, then the percent of nitrogen in silver nitrate is 14.0067 grams of nitrogen, right here, in 169.8731 grams of silver nitrate. And then finally, for the percent of oxygen, it's 47.9982 grams of oxygen in 169.8731 0.8731 grams of oxygen and times 100. Okay, that's all percent composition is. Okay? What now? Oh, I'm sorry, it should be AgNO3, right? Okay? Alright, that's all it is. It's really simple. Okay? Alright, so this is just stoichiometry, okay? Only instead of doing mass to mass, you're going to be taking the volume of fluorine gas and getting to the mass of the fluorine gas at the end, okay? So one of the two mass to mass problems is not a mass to mass problem, but a volume to mass problem. We're going to assume that fluorine gas is at STP for that part of the process. Now, you listen, and then the percent composition is what I just showed you. That's this, okay? But for silver nitrate, which is one of the two compounds, you've got to find the molar mass for anyway in this problem. When we're converting from volume of a gas to moles of a gas, this is the equality statement you want right here. Volume of a gas to moles of a gas. Volume of a chemical in gas, when it's a gas, as long as it's STP, the moles of the chemical, use molar volume, and this is the molar volume. So you've got this equality statement already written out for you. All you have to do is memorize the fact that 22.4 liters of a gas equals 1 mole of a gas, and then you build conversion units the way you've been taught to do it all year long. We even talked about this when you did your mole project. It was one of the requirements of the mole project that you look up and include this relationship between volume of a gas and mole of a gas. So this should not be hard.